Thank you very much for that kind introduction. And thank you for welcoming me here this morning. I thought it would be interesting to spend some time talking about some of the things that we are thinking about in commercial airplanes at Boeing as we anticipate the design and development of the next new airplane. I reflect back to the beginning of the 787 program when my team was tasked with not just designing the airplane, but designing the cockpit as well, and designing a cockpit that honored all of our previous experience designing cockpits, and which honored all of the previous flight crews and flight crew capabilities that were part of the design and development of Boeing airplanes. This is a photograph of how the 787 cockpit turned out. It's a wonderfully efficient, comfortable flight deck, and the 787 today shares a common type rating with the 777 aircraft. But there were a number of improvements that came along with the development of the flight deck, including as basic equipment, a dual head-up display for increased situational awareness, because as we began to realize situational awareness was beginning to play a more important role in the safe operation of airplanes. When I reflect back on the flight deck philosophy for the design of all of the flight decks for modern commercial jet transports at Boeing, it comes down to a couple of key points that guide our flight deck design. First, the pilot is the final authority for the operation of the airplane, not the software, the pilot. Both crew members are ultimately responsible for the safe conduct of the flight, working together, not just the captain, both crew members. Flight crew tasks in order of priority are safety, passenger comfort, and efficiency. We design for flight crew operations based on pilots' past training and operational experience. We design the systems to be error tolerant. The hierarchy of our design alternatives is first, simplicity, second, redundancy, and lastly, automation. We don't automate that which is complex. We make it simple first, we make it redundant, and then we automate if appropriate. We apply automation as a tool to aid, but not to replace the pilot. We address the fundamental human strengths, limitations, and individual differences for both normal and non-normal operations. And we use new technologies and functional capabilities only when they result in clear and distinct operational or efficiency advantages, and there's no adverse effect to the human-machine interface. Now, these philosophies have served us well for the last 50 years, and as we look forward to an environment where air traffic is growing dramatically year after year, and the number of pilots that are available is decreasing, and in particular, pilots with the same levels of skill that they have today is decreasing even faster. It causes us to look back at those flight deck philosophies, and it forces us to revalidate each one of the assumptions that drove those philosophies. Just 2 years ago, there were over 37 million flights operated in the commercial air transport system around the world, and that number is increasing year after year. 37 million in 2014, and that number increases year after year. And yet, as we look forward, the number of pilots that will be available do not support that continued rate of growth, and specifically not pilots with the same levels of skills that they have today. So when we look back to these flight deck design philosophies, we have to ask questions about whether or not each one of these still remains valid, and we're going through that process today. For example, you can see the second bullet, it says, both crew members are ultimately responsible. The philosophy then assumes that it requires 2 crew members. And yet, in a world where the number of airplanes and flights is going to keep increasing and the number of pilots is going to decrease, perhaps it doesn't need to be both. Perhaps it needs to be one, and the appropriate level of monitoring and safety services on top of that. And we have to think our way through that. Automation began a long, long time ago. Our first experience with automation at Boeing was the Model 247, where the first Autopilot was introduced. Only 10 of these airplanes were built, and the advent of the Second World War really stopped the development of the 247, or the deployment of the 247, but we learned a lot about autopilots in the process. How automated are airplanes of today? Well, clearly we've automated navigation, flight management, thrust management, communication, auto land, airplane health monitoring and reporting. Some of these are automatic and some are autonomous. And the difference, I think, between those two is when I think of an automatic function, it's a function where when you initiate it, it completes a series of pre-programmed tasks in order, the same time, every time. Autonomous means the system has to correct itself for outside influences. A really good example of that is Autoland. We have almost perfected the Autoland capability of our aircraft today. In fact, the 8th landing of the 787 was a GPS auto landing. The 8th landing ever of the airplane was a completely autonomous GPS auto landing. Now, there was a flight crew member, there were 2 flight crew members in the seat monitoring, but it was an autonomous landing of the airplane itself. The system responds to external disturbances, it responds to errors in the equipment on the ground, and it responds to errors in the equipment on the airplane, and it makes decisions on a real-time basis about how to safely continue the landing. And that, to me, is the difference between autonomy and automatics. However, for non-normal events, many of these are not provided today autonomously. For example, collision avoidance and ground proximity avoidance. While the system can alert the flight crew of these things, the flight crew has to step in and intervene to allow the airplane to complete its task safely. And now I think I have to decide, are we going to, we can keep going? Okay, all right. So in this case, you see collision avoidance and controlled flight into terrain avoidance. These are things that as we continue to automate the airplane, we have to think about whether we automate the response to a TCAS alert or we automate the response to an enhanced ground prox alert instead of simply alerting the crew to those conditions. There's a lot of media press today about driverless automobiles, particularly in the United States with Uber, Google, Amazon, Tesla. And in fact, earlier this year, there was the first documented death as a result of a Tesla Autopilot accident in one of the cars. It was very interesting for me to watch the response of the regulators and the media because that could have gone either way. It would have been very easy to overreact and not allow any of these trials to continue. But in my view, there was a very measured reaction by those involved, which allowed the technology to continue to be deployed. And I wonder if there had been a similar type of accident in aerospace, whether or not that same measured approach would have been followed, because the media seems to pay much more attention to what we do in aerospace. When I reflect on highway safety in the United States in 2015, there were 35,000 fatalities from automobile accidents on our freeways. 35,000, and that was a 7% increase from the previous year, and it was the largest year-over-year increase in the US in nearly 50 years. And so when I think about, people ask me, well, when will Boeing automate its airplanes fully? Because we're already automating automobiles. Well, 35,000 fatalities, and there were 0 in commercial transportation in 2015. 0. And that's a really tough number to beat. So if you're looking at automation of automobiles, for example, driverless cars, it's much easier to improve the level of safety of driverless cars when you're starting from a level of 35,000 fatalities. In aerospace, you're starting from a level of 0, and you have to be as good or better than 0 to improve safety, which is a difficult assignment. we recognize that any move towards autonomy has to be neutral or better from a safety perspective. A typical regulatory approach says that whenever anything is new or novel, it must be better than what came before. Not as good as, but better than what came before. And compensating features must be understood and provided. That's captured in how we try to achieve equivalent level of safety rulings on a design feature. While it's an equivalent level of safety, it must be accompanied by a compensating feature that in reality makes it more safe than strict compliance with a rule. Okay, so the autonomous aircraft market is a very, very big market. It's huge, it's growing rapidly. Over the next 10 years, we expect $82 billion in sales, significant growth in China, India, Asia, Europe. The US regained the #1 export position in 2015, followed closely by Israel. This is a very, very big market. And at Boeing now, for the first time, we're really thinking about whether the Boeing commercial airplane company has anything to do with autonomous aircraft and what the relationship is between the two of them. I see my IAI friends here. We've spent many hours talking about the future of this technology and where is the right spot to introduce this technology. I think back 70 years ago this year, 70 years ago, Boeing won the contract for the B-52. It's hard to believe that it was 70 years ago in 1946 when Boeing won the contract for the B-52, and there are still more than 80 B-52s flying in the world today. They've been upgraded and they will probably remain flying until the 2030s. But that airplane flies with 8 jet engines. 8 jet engines. It was followed by the 707 and then the 747, which crossed the oceans with 4 jet engines. And then we introduced ETOPS and the ability to cross oceans and fly long distances with less than 4 engines. But we didn't go to 3, we went all the way to 2. And there were a lot of people who asked the question about whether we needed to go to 3 before we took on the additional risk of going to 2. In some ways, I feel like we're at the same crossroads in commercial aviation today, because we recognize that with a pilot shortage and with an increase in the number of airplanes, we will have to do something that addresses that. Does that mean that we go to 1 pilot, or does that mean that we go to 0 pilots? And that's a real question that we're struggling with today. And we also recognize that if we do go to 1 pilot, we have to be prepared for the inevitability that we will at some point be faced with 0 pilots. Because at a rate of about 10 to the -5th, pilots are incapacitated today. We realize that pilots, every year, there are several pilots that have heart attacks or die while they're flying an airplane. And so if we were to deploy a technology that allowed a single pilot to operate one of our commercial jet transports, we have to be prepared for the inevitability that that pilot will be incapacitated, and we have to be able to safely recover that flight without that pilot operating the airplane. This presents, as you can imagine, a number of great challenges as we think our way through this. There are many remotely piloted or autonomous aircraft today. Here are some examples of airplanes that Boeing has been involved in. Most recently, the deployment of the Q F-16 fighter, which has been provided with autonomous capability by Boeing and being deployed by the Air Force now as a target airplane. We also think about perhaps the simplest way to do this is to approach it with a freighter first, because there is a much more acceptance of risk by freight operators than there are by commercial passenger operators. And as you can also see from this airplane, this potential future concept meets my goal that I'd like to someday design an airplane that's so ugly no pilot would ever want to fly it. So there are a lot of challenges that we have to overcome to be able to allow single or 0 pilots in the flight deck. Sense and avoid capability, upset recovery, automation failures, and interoperability with less capable equipment. I've picked a couple of photos to illustrate this case. On the right side in the top, you see a 787 landing taking off, at La Paz, Bolivia, where the field elevation is over 13,000 feet. And that's a case where when an airplane approaches to land in Bolivia, rather than repressurizing for the descent, the airplane has to depressurize for the descent from a 6,000-foot elevation cabin to a 13,000-foot elevation cabin. And the automatics in the airplane have to allow that to happen because you don't want to open the door on an airplane that's pressurized. There's the optimized workload constraint. The airplane would have to be capable of automatic taxi, automatic takeoff, and automatic landing, and not just automatic landing in perfect conditions like we have today when a Cat 3 auto land is initiated, but in a crowded environment where things aren't perfect and things are going on all the time. Managing the systems on the airplane, managing the flight plan and the altitude, and being able to intervene when you have to change the flight plan on the fly tactically rather than strategically. And then finally, the reliability and the integrity, not just of the airplane and the systems on the airplane, but of the link to the airplane and the connection with the ground and the security of the supporting software on the ground. To be able to allow any type of control from the ground, we have to have a link that is so secure to the airplane that the integrity of that link is never called into question. It would be very, very difficult for us to continue operating an airplane if there are rumors of cyber breaches to that airplane or if there are actual cyber breaches to that airplane. Today, none of the Boeing commercial airplanes have a control link to the ground. While we do have data links that go from the airplane to the ground, none of those are capable of supporting the control of the airplane from the ground. The control domain and the network for the control domain on the airplane is completely independent of that off-board link. And so it would be impossible for someone from the ground to take control of an airplane today. As soon as we build that capability into the airplane to allow an incapacitated pilot to have control taken over by the ground, or for complete autonomous operation, we're introducing a link that could cause a cybersecurity threat, and we are also introducing a target that hackers will go after immediately to try to prove that they could control an airplane. So these are things we have to think about if we start to go down this path. Managing the network in the airplane and the network on the ground, and being able to override any contingency that could happen in the air if a pilot is incapacitated. So this is a really difficult challenge for us, and we at Boeing have to enter it very, very carefully. We have to understand what the technologies are to build our research projects so that we're ready when this eventuality comes. There's gaps in the system today. When I look at the design of an airplane, our airplanes are 10 to the minus 9th from an integrity perspective. But more than half of that level of safety relies on the flight crew to be monitoring the airplane and being able to step in and take over in case of an event that wasn't anticipated. And I see this all the time. It never turns into a big event. It's always something small, but every week in our fleets right now, the flight crew steps in and intervenes when the autopilot disengages for an unknown reason, when an airplane makes a left turn when it's supposed to keep going straight. We never hear about these things because the flight crews are able to step in, take over, correct the situation, and move on. We learn about it through the continuous operational safety program. We make whatever design changes are required. This is a system that has worked for 50 years and has continued to make aviation safer, and it will continue to make aviation safer. But if we're going to eventually go from 2 pilots to 1 pilot and eventually to 0, we need to make sure that we're taking positive movements in the direction of safety and that the airplane remains at a 10 to the minus 9th level of integrity. Government and industry collaboration is a must for this to work. The regulators must provide technical and regulatory standards, policy guidance, and operational procedures that allow us to evolve this capability and mature it together. The global standards must encourage cost-effective harmonization so that we aren't doing this on our own, that we're doing this with other airframers, with other governments, with other regulators in an ICAO-like environment in a harmonized way. An industry needs to accelerate the momentum of the current progress in order to make autonomous capability possible. We've been moving very, very slowly. And people ask me all the time, when do you think autonomous operation will happen in commercial transportation? And I say to them, I know two things for sure. The first is that it won't happen for another 30 years. And the second is that I'm wrong. I don't know how wrong I am yet, and I'm still trying to figure that out. My wife tries to tell me every day how wrong I am. But anyway, so we have to work these things as an industry together, and we're very excited about starting down this journey and trying to understand what the issues are, where the gaps are, and trying to resolve them. So with that, I'd like to say thank you very much for your attention. I really look forward to jumping into this problem and trying to understand it more. And I enjoy working with many of the folks in this room already on some of these tough problems. So thank you very much.